Okay, we can start. So, good morning again. I'm glad to see everyone again. Today we are attending the third lecture given by PhD Ahmed. The name of the lecture is Dynamic Walking Control Towards Human-like Walking. I leave the microphone to PhD Ahmed.
Okay, thank you very much and good morning everybody and welcome again for this lecture. So today I will try to talk about another application of control engineering, and today we will try to talk about humanoid robotics. So the idea is to design controllers to reproduce the human walking on a humanoid robot. So actually, since yesterday I have presented this first part concerning my lab, I will try to skip this part. So I am coming from a laboratory situated in the north of France, in Montpellier. We have 5 research teams in this research lab working on different aspects of robotics. We have many experimental platforms within this building, and actually today I will focus my lecture on biped and humanoid walking robots. Here it's just a summary of my research activities, and actually I'm working on control of robotic systems with mainly 4 applications, and today I will focus the presentation on humanoid walking robots. Now let's go in the details of the presentation. Here is the outline of the presentation. So I will try to start with an introduction, then I will talk about a brief historical overview about humanoid robotics. I will introduce the context and the problem formulation concerning control of this kind of systems. Then I will try to present our experimental platforms. So actually we have a biped walking robot called Sherpa, and we have 2 humanoid robots. So all these 3 experimental platforms will be used to validate the proposed control schemes. And then the most important part is the proposed working control study. It's a study since it contains different steps, and I will try to detail all these steps until we get to the experimental results. And I will conclude the presentation by the end. So first of all, and to understand, I think this slide is very good, and I thought it was good to introduce this slide in the first lecture. Why? Because it's a very basic classification of robots in general. Actually, so if we are interested in robotics, so the first question that we can ask is the following: is the robot a manipulator with a fixed basis, or it's a mobile robot? So if we answer to this question, we can have 2 classes. The first one is the class of robotic manipulator arms, and the second one is the class of mobile robots. So in the first class, they are characterized, the robots within this class, by a basis which is fixed. So like the shoulder here, and the manipulator can move in the space. And then depending on the mechanical structure or the kinematic structure of the manipulator, we can have 2 classes or 2 subclasses, which are serial manipulators and parallel manipulators. So the first lecture was on these parallel manipulators, and I have explained the difference between serial and parallel manipulators. Serial, it means that you have joint body in a sequence way, going from the base to the end effector. Joint, body, and so on. And parallel, you can put at least 2 arms in parallel to have a parallel manipulator arm, or parallel kinematic chain. Then now let's see the second class. And the second class here is the class of mobile robots. And in this case, we have no restriction about the base. So the base can move in an environment, and then now we can ask the question, what is the environment of evolving of this platform, or where this platform can evolve, and we can have 3 kinds of environments. So the first case, the robot can move on ground. So we have ground robots. The robot can move in the air, flying robots or aerial robots. And the robot can go underwater. So we have underwater robots. So this is the 3 subclasses of mobile robots. Now let's see the ground robots class. And now we should ask another question. What should be the locomotion mode used for the ground robots? So we have 2 kinds. So the first one is what we call wheeled mobile robots, so they use wheels to move on ground. And the second class, they use legs, so we call them legged robots. And then for legged robots, we can also ask the question, the robot will use which number of the legs, 2 or 3 or 4 or 6 and so on. And depending on the number, we can have bipeds, so robots who have 2 legs only. We can have the class of quadrupeds, so 4 legs, and 6 legs, we have the class of hexapods. So this is the class of mobile ground robots, and then we have the class of underwater vehicles. I have introduced them previously in previous lectures, and aerial vehicles or flying robots is the last one. So this is just to give you an idea about the simple classification of robots to understand where we are. So actually, I give a lecture on parallel robots, I give a lecture on underwater vehicles, and actually today I will give a lecture on humanoid walking robots, biped robots. Nice. Now, let me talk something about bio-inspired locomotion, because previously here I talked about locomotion, and I said here for the legged robots, they use legs to move. And now we have bio-inspired locomotion for different kinds of robots, not only legged robots, but for flying also, for underwater and so on. Let me just give you some examples of bio-inspired locomotion, and the first bio-inspired locomotion can be bio-inspired from human. So we have the case of humanoid walking robots, so they have the same morphology as the human, they have 2 legs, and they can walk, they can do many tasks like a human. Now, for this kind of walking or locomotion, biped locomotion, there is not only human, there is other kind of animals that can be bipeds also. And as you can see here for this example, you have birds. Birds, they have only 2 legs, they can walk also. And as you can see, you can create some robots that are bio-inspired from birds, and they are also bipeds. Now we can have other examples using 4 legs, the quadrupeds, and as you can see here, 4 legs to reproduce this walking like animals, for instance. Another locomotion, it can be not walking but hopping. So to hop here also we have another example of bio-inspired locomotion, like the kangaroo here, so we can create some robots that can make the same motions. And here, as you can see, it's the same morphology and also the same kind of motion. Another kind of locomotion here is flying. Flying also, there are many examples of flying birds or flying birds robots. See, it's exactly the same morphology as a bird, and they use wings also to move. Other examples for underwater, I have talked about this example in the previous lecture. So this is what we call bio-inspired underwater robots. So here, as you can see, is the morphology of the fish. They have fins, they can move exactly the same as fish. And we can have also more examples, like for climbing robots, they can climb. So also we have this kind of locomotion. So this is just to give you an overview. So now I am interested in this class, the class of biped walking robots. Let me introduce you now to humanoid robotics today, and I give you this first example. This is just a very simple example. It's a real robot. So few months ago I were in Thailand, and I have been invited to visit a research laboratory there, and they have invited us in a Japanese restaurant. And as you can see here, you can be served by robots, not humans, but robots. So here the robot, it's a classical humanoid robot, but it is on a mobile platform, and the robot you can order what you want to eat, and in a few minutes the robot will come and will bring you what you ask. Another example of humanoid robots today, this example. So this is example, as you can see, there are many prototypes. These prototypes are coming for Boston Dynamics. So Boston Dynamics, they have designed many prototypes, and one of them, it's this one, Atlas. And as you can see, it's a biped walking robot, so it can move outside, and it is impressive the degree of stability of walking of this robot. So as you can see, it's even walking on snow, and it is very stable, and it keeps its balance, and it avoids falling down. So, and this is, pay attention, it's not so easy, since in our case for human it's already difficult. So for robot, it should be more difficult. So the robot is very powerful, and the stability of working also is very nice in this case. So it is equipped with very powerful hydroelectric actuators, and he can keep its stability while walking. And also it is characterized by another thing which is interesting also. He can move some heavy loads, he can carry loads like that. And this is also a typical feature of this robot. So this is the second example, and I will show you a third example of humanoid robots of today. And you will see it's also a very successful humanoid robot, perhaps you know it. So we will see the video just after this one. Actually here it's just an external disturbance to see if the robot is able to keep its stability. And he used here the camera to localize this object. So he wants to take this object, and the human here try to disturb it. And you can see also the degree of autonomy when he moves the box. So the robot is following the box until he gets very close to the box to be able to take this box. And now it's a big disturbance, so the robot is falling down, and then as you can see he is able also to get to the vertical upright position, and as you can see here how it works. So he can open the door, he can close the door, he can walk, he can manipulate objects, he can carry loads, and so on. Nice. So this is the second example. Now let me introduce another example. It's the third one.
I've been to Honda's technical studio in Brussels to meet one of their most...
And it's coming from Honda. It's a Japanese company manufacturing cars, but actually they manufacture robots also.
Who I was about to meet wasn't actually a human, but a robot. Honda's famous humanoid robot, Asimo.
Its name is Asimo.
Asimo has been designed to interact with humans. So
this is very important, the interaction with the human.
Sensors in its palm detect your touch, while cameras in its head.
Face detecting, so it uses the camera.
Stabilization technology enables it to react if you upset its balance. Moving
and the balance, the equilibrium, to get the equilibrium, or to keep the equilibrium of the body.
This latest version of Asimo is the product of...
Here is the history of developing of this robot.
Started back in
1986.
A robot which could walk, albeit very slowly and clumsily. In 1988, it was developed to walk more like a human being.
Second one.
And in 1993,
the third one.
By 1996,
96.
the robot had become intimidatingly large. So in 1997, it was shrunk to a less threatening size. Thankfully, before being made autonomous. In 2000, Honda...
2000 is the last one.
Stands for Advanced Step in Innovative Mobility. Standing 130 centimeters tall, which is the same height as a seated adult, it's the perfect size for helping out around the home. Over the years, Asimo has been constantly developed, and it's now mobile enough to play sports. However, it's wise to warm up before any physical exercise.
So he can walk,
if you're a robot,
he can run,
and as well as run at 6 miles an hour, Asimo can walk backwards and hop.
He can hop also.
You can also kick a ball, so
kicking a ball, it's very easy for him also, as you will see.
That's 1-0 to the Autobots. But is Asimo as good at saving a shot as it is at taking one? Looks like Honda hasn't trained Asimo to be a goalkeeper just yet. Football is thirsty work, and thankfully Asimo can get...
Another feature, this robot is equipped with 2 arms, so he can manipulate objects, he can do the co-manipulation of objects, and he can help the human, for instance. Here I have an example.
It's an incredible achievement for a robot.
And he manipulates the object exactly like the human, as you can see. Interaction with the human here. and he give him the cup.
In total, Hacia has 57 degrees of freedom, and this allows it to dance, while its 52 volt battery can keep it going for 50 minutes. Looks like this robot actually has a better than some humans. Anyway, for that. Well, so I've got to go now. It was very nice to meet you, and don't forget to write an email or whatever it is that robots do.
Anyway, so these are just 3 examples of robotics, humanoid robotics of today. So I have just introduced them to understand where we are actually. Now let me introduce just a brief historical overview of creation of this kind of robots. So here just the first dates created, regarding robotics in general and humanoid robotics particularly. So the first time where the term robots was coined, it was 1921. 41, so it's the Asimov who introduced the 3 laws of robotics. So 1994, the works of Wiener, for instance, in cybernetics. 69, so the work of Viko Trabovich concerning the humanoid walking, concerning the stability of walking. So he introduced a very interesting concept called the ZMP. It's the zero moment point. I will introduce it later on. It's a very important concept in humanoid robotics, since using this concept you can prove or you can guarantee the stability of the walking of the humanoid robot. Then 1973, so the first robots coming from Waseda University, and then during the 20th century many prototypes have been designed, as these examples as you can see here, P3, Asimov for instance, and many other prototypes. And actually during 21st century further additions were added to other prototypes, and mainly the last prototypes are human-like humanoid robots. Here is just a summary of the different prototypes for 2 manufacturers of these robots, Waseda University and Honda. We have seen in the previous video the different prototypes here from Honda, and the last one is Asimov. And for the Waseda University also, they have the same, they have followed the same procedure, since if you see the beginning, the first prototypes are only lower limbs. So there is no torso, no arms. Why? Because we think that, for instance, to reproduce the human walking, you need just the 2 legs. You don't need the upper limbs. Yes, you can add the upper limbs. They can help for the stability of walking, to improve the performance and so on. But it's enough to reproduce this biped locomotion. This is why they start with just biped robots, and finally they go towards human whole body prototypes. Now let me introduce the context and the problem formulation concerning my research activities regarding this topic, and the idea is to reproduce the human walking on a humanoid robot. So first of all, as you can see here, we have these 2 videos. The first video, it shows the human walking, and the second video, it shows here a humanoid walking. So through these 2 videos, we can see and you can compare the obtained movement of the motion. As you can see, the human walking is much better than the humanoid walking, because the humanoid is walking something like that, and the human is very powerful, very smooth. The motions are very smooth, so it's much more performant. Now, if we are interested to reproduce a human-like walking, so the first idea is to analyze the human walking cycle. So there is a cycle. Why? Because the motions are periodic, so we repeat the same motion periodically. And if we look to the human cycle, it can be summarized by this picture. So when we walk, we have different phases of walking. And mainly, we have 2 main phases and 1 instantaneously phase. So the main phase is what we call the single support phase. During this phase, we have 1 leg in contact with the ground, and the other leg is doing this swing of motion. So this is what we call the single support phase. Then, by the end of this, when this leg touches the ground, we have the impact phase. The impact phase is the instant where the leg touches the ground. And this phase is instantaneous because it is very short. Then the next phase is the double support phase, and during this phase we have the two legs in contact with the ground, and we continue swinging up the body of the human. So if we want to control or design controllers to produce this motion, we can represent mathematically this model like that. So we have three phases here, as you can see, the main phase of single support and double support, and the impact phase, which is instantaneous. Now, if we look to the literature, so many research works have been done, and mainly they consider these different phases. They consider this one, and this one, and they design a controller for this one, a controller for this one. They consider that this one is a disturbance, and they try to keep the stability of the working of the cycle. Now, human working, pay attention. You think that it's very easy. Pay attention, it's a very difficult task. It's not so easy. And here, this is just a simple example that shows you that it's very difficult. So maybe when he starts working, so as you can see, he cannot concentrate on many things at the same time. And just doing one step, it's very difficult for him, since he has to keep this stability of working, so the equilibrium or the balance during walking, and also here he tried to catch this object. So this is very interesting to know. So it's a very complex task. And also pay attention when we walk. In our case, the human has many muscles. So they have many muscles, and as you can see here, the different muscles and their activation, they're working. So when you do this periodic walking, so each muscle will be periodically activated or deactivated through the walking cycle, as you can see here. And this is just to give you an idea about the human walking, and to say that it's very complex task, so it's not so easy to reproduce this task on a humanoid robot. Now, as I said before, so if you are interested in controlling humanoid walking robots, so we have to see to the working cycle, and the decomposition of the working cycle is, as I said before, single support, impact, double support, and so on. And now we have to design a controller for the different phases and to keep the stability of the humanoid robot while working, to avoid falling down. But now the question is what we need. I want to do this, what we need to do this task of working on a humanoid robot. So to answer this question, first of all, we have to ask another question to answer what we need to do this walking. First question is, we should do a static or dynamic walking. So we have two kinds of locomotion, of gaits, of walking gaits. So the first one is static walking, and the second one is dynamic walking. I will explain the difference. It's very easy. So the first example here on the left, it shows a static walking of a biped walking robot or a humanoid robot. So the idea here, as you can see, there is a constraint to keep the balance and the stability of walking. And the constraint is very easy. You have to keep all the time the projection of the center of mass under or inside the polygon of support. What is the polygon of support? If you have here two legs, so you have just to construct the area, including the 2 foot here, the 2 feet, and this is the polygon of support. So when you walk, you have to keep all the time the projection of the center of mass that you can see here. It's the black square, and you keep it all the time inside. If you want to do a step, what you have to do? You have to move a part of the mass of the body in this direction, such that the projection will be only in this first leg, this first foot, and then you can move, and you will be stable because the projection will stay. Here, as you can see, it will stay inside the polygon of support of just one leg in contact with the ground. Then you have to move to the other leg and to repeat the same motion. So there has been many robots developed based on this basic principle of the static walking, as this one. As you can see here, you have two big muscles on the torso, so they move this in this plane, to guarantee that the projection will be inside 1 foot or the other one, to do, I mean, with security, the leg, the step, avoiding falling down. Now, this is the static walking. And the case of a robot with many legs, so you have just to construct the polygon of support, it's the polygon relating the point of contact with the ground, and you have to ensure that center of gravity or center of mass, its projection is still all the time inside. So if you move one leg like that, the projection is still inside and the robot still be stable. And it's very easy to do this kind of walking, but the problem of this kind of walking that you cannot do a high-speed walking or dynamic walking because it's static. You have to do something like that, like that, like that. This is the static walk. Now, if you look to human, in our case, we have no these constraints. We cannot do like that to walk. No, we walk directly like that. When we walk like that, if you see the evolution of the center of mass, the projection of the center of mass is here, as you can see, sometimes it's outside the polygon of supports, and sometimes it's inside. Where it is inside? If the two legs, like that for instance, the projection is inside. If I do this, it's outside, 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 up, inside, outside, outside, inside, and so on. So we have different phases, and alternatively, in a static way, we have stable and stable, stable and stable, stable and stable. But if you look to the whole walking cycle, it's stable because the robot will not fall down. It's unstable. When it touches the ground, it becomes stable. And unstable, it becomes stable, and so on. But this kind of walking is much better than the static walking. Why? Because we can go, the speed can be higher, the dynamics can be better, and the walking can be more performant. Now, here, as I said before, the idea is to compute what we call the center of mass, and we compute the projection, and we keep it inside the polygon of support. Now, for dynamic walking, we will not use the center of mass. We use another concept, and this is the concept introduced by Viktor Trabovich in 1969. It's called the ZMP. ZMP is coming from zero moment point, and to understand it's very easy. If you have somebody with contact with another body, you compute the contact force with the ground, vertical contact forces, and you compute the resultant, so the big force that's including all the forces. Its position, it represents the position of the ZMP. And the idea is to keep this position of the resultant vertical forces inside the polygon of support during the walking. So you can have walking like this, where the center of mass is outside the polygon of support, but the ZMP all the time is inside. So we can guarantee the stability of the dynamic walking. Nice. Now, to answer all the questions, what we need to reproduce a human walking on a humanoid robot, here I can show you just an example. Don't worry about the contents inside. So I have just to emphasize three things. This is a control algorithm or control scheme, if you want, and it includes three things, three main things. Here it's the controller itself. Here it's the pattern generator. It's the trajectories. I want to do motion, periodic motion. How we will generate these trajectories, this motion. This is what we call the pattern generator. And the last one, it's what we call the stabilizer. And the stabilizer, you know, it's also another controller. It's like if you have an inner control loop, an outer control loop. And the outer control loop, it represents the stabilizer. And the stabilizer, the idea is to keep the dynamic working stable all the time. This is the idea. And the inner controller here, inner control loop, the idea is to follow the reference trajectories generated by the pattern generator. So to answer the question, we need two things. We need to design a pattern generator, and we need to design a controller. The controller, it includes the tracking controller and also the stabilizer. Nice. Now I have answered the question how and when, how we can reproduce human walking on a humanoid robot. Now let me introduce the experimental platforms that we have in our lab and on which the proposed controllers have been validated. I start with this first one. This first one, the robot is called Sherpa. Do you know what is a Sherpa? The name Sherpa. Very easy. This is a Sherpa. A Sherpa is a human. And what is this human? It's a people from Tibetan who serves as a porter in mountain expedition, in mountain climbing expedition. So they help expeditors, they are guides, but they have specificity, they carry loads. This is the idea. Now, why we call our robot Sherpa? We call our robot Sherpa. You know the idea when we design the robot is we want to design a robot which will work at the university. When the secretary receives a box for a professor, for instance, so she will put the box on the robot, she will start walking, the robot will use the vision and will follow the secretary until she will arrive to the office of the professor. The secretary will take the box and give it to the professor. So this is the idea, and this is why we call it Sherpa. Now, how this robot was designed? So this robot was designed in a research project in collaboration with a biomechanics lab in France, in another city called Marseille, and we have asked them to help us to choose the minimum number of degrees of freedom per leg to reproduce the human walking. So we asked them a very easy question: what would be the minimum number of joints per leg to be able to reproduce a human walking? So they made the study, and the study, this was the result. So they told us that you can reproduce the human walking through 6 degrees of freedom per leg. So we have 6 and 6, and the whole robot will have 18 degrees of freedom, since it has 6 and 6, and the position and orientation of the robot in the space, so it has also 6, so 6 and 6 and 6, so we have 18 degrees of freedom. And also we tried to design a robot which is bio-inspired in terms of actuation. In human actuation, we have the leg and we have the tendon. The tendons, they are antagonistic and they actuate the leg. We tried to reproduce the same concept here using cable differential joints, an actuation system, to actuate 2 degrees of freedom at the same time. So we have 2 motors to actuate, 2 and 2 others and 2 others, 6. So 3 block of actuation. And we have this very important feature. This is what we call the transparent actuation. It means that we have low inertia and back drivable. What do we mean by low inertia? It's easy for you to understand. Low inertia, but back drivable. If you see the previous robots, Honda for instance, when you cut all the control inputs, all the currents, the power and so on, and you try to move the leg manually like that, you cannot. It's not possible. Because it's not back drivable. So the robot is back drivable if there is no control inputs, no current, no something coming from the actuators. If you want to move it, you can. This is what we call by back drivable. And where we want to use this, why we try to propose back drivable actuation for the robot, if you look to the human walking, when we walk, during this swing phase, mainly we give a very, very small amount of energy. What we will use is the gravity. We use the gravity and we will swing the leg based on the gravity. So we try to reproduce this based on this kind of actuation on the robot. This is the idea. Now, this is the result of the mechanical design of the robots, as you can see. And we have constructed mechanical parts here without the electronics. And the final prototype is here. So it has 2 legs, it has a computer to control everything, and it has also the power coming from outside. This is just some pictures regarding this prototype Sherpa. You can see the control, you can the hip, the femur, the knee, the tibia here. One thing which is very important here in the feet of the robot is how we can evaluate the CMP. As I said before, if you want to do dynamic walking, you need to keep the CMP all the time, this resultant force regarding the Z-axis, all the time inside the polygon of support. But the question is how you can measure this. So to answer the question, it's here. So each foot of the robot is equipped by a 6-axis force sensor. So we can measure 3 forces and 3 torques, Fx, Fy, Fz, and tau x, tau y, tau z. So through this measurement, we can localize the resultant force, and we can localize the position of the ZMP. So this is very important. And here, as you can see, just the cards, the electronic cards used for the control of these motors. The second prototype. It's a Japanese robot called Hope 3. As you can see, it's here. So it's a whole body robot. So we have the 2 legs, and we have also the upper body, the torso, and the 2 arms. This robot has 28 actuators, 7 DC motors, and 21 DC motors and 7 steppers. Each joint is equipped with an encoder to measure the joint positions. It has 4 sensors also the same, but it's different from the previous one. Previous one has just 1 sensor, 6 axes. Here it has 4 sensors in the foot, and then by combining these forces, we can compute the position of the CNT. It has USB cameras, it has a distance sensor, a speaker. It has also inside what we call IMU, inertial measurement unit. This is in case where the robot is falling down, you can detect this based on the measurement coming from the IMU. And also it has grippers, and we can use this to demonstrate or validate the control approaches for whole body control. The last one. The last prototype is now. It will be presented through this video. So now it's a French robot. So initially it was created by Aldebaran. Aldebaran, it's a French society who created this robot. And here they present how it is, this robot. So it has tactile sensor here in the head. You can see also the size regarding the human, approximately the size. So 58 centimeters. You can see how the robots can walk, for instance, it's moving. Some of the features also we can see them in the video. They are coming. Bumpers here, he can detect objects when he touches them. Using this, he can use the camera to localize objects. Thanks to these 2 cameras, so we have the stereo vision system. And then he can try to get this object, for instance, using the grippers. Or using the hand, it's like the human. And we control this. Then he will use the camera also, he can use the camera to localize objects. And he will put this object inside. This is just an illustration to see what we can do using this robot. So if you have more than 1 robot, you can have a communication between 2 now robots. Here you have 2 robots now, and they can communicate between each other.
Hello now, 41.
So this is the communications, it can be infrared, Wi-Fi, or voice. So 3 kinds of support to communicate between 2 humanoid robots now. He has also legs, as you can see. Oh, the same problem as previously. So if he falls down, he has the possibility to get in the upright position, as you can see. He has just to execute this motion. And as I said before, IMU, this is the inertial measurement unit which is inside here, that helps you to detect this falling down, such that you can prepare yourself to avoid to break the robot. So he prepared himself to get to the good position while falling down.
Goodbye.
That's it. So this is now, and unfortunately this company was bought by a Japanese company, and actually this robot is becoming Japanese. Okay, this is just a remark. Now let me talk about the proposed walking control strategy or study that we have proposed in my case. So as I said, the idea is to reproduce the human walking. What would be the proposed study? We have proposed different controllers, and we have made experiments on different robots. So on Sherpa, on Now, on Hope3. And let me now just detail one of these control solutions. It's the hybrid kinematic dynamic control. I explain. If you see to the literature of control of humanoid walking robots, you can find 2 different kinds of controllers. You have kinematic control and dynamic control. Kinematic control, it is based on the Jacobian matrix in robotics, and dynamic control, it is based on the dynamic model. So in our case, we have proposed a solution that combines both of them. I will explain how. So in the following, so we have made a study. We tried to generate a human-like walking on this humanoid robot. So we made this study following these 5 steps to get to the final result. And these final steps are, first of all, simulator. We try to simulate before we try on the robot. Human walking study, we try to do something human-like, so we have to study the human walking. So this is the second step. The third step is the generation of the reference trajectories to do this walking. This is the pattern generator design. The fourth step is the controller itself, the control architecture. And the last one, it's the tests or the implementation on the humanoid walking robot. Now I will try to detail these 5 steps. So the first step, we have developed the simulator. So here just some features of this simulator. So we have used the C++ language. We have included inside the model of the Sherpa robot and other models. And we have introduced also the contact with the ground. We have introduced 2 kinds of contacts, a rigid contact and a compliant contact. Rigid, it means that 2 bodies are rigid, and compliant is like spring. So these 2 kinds of contact models. So we have used OpenGL, C++ language, and we have designed this simulator as a modular approach, such that if you want to add other modules, it's very easy to extend the simulator. Here, we have introduced the CAD view or CAD model of the HOPE3 robot inside the simulation of this. And here we have introduced a 20-degree whole body model. It's just a model of a robot like that with 20 degrees of freedom. And also we have introduced others. This 20 degrees of freedom model is here. As you can see, the different degrees of freedom. And as you can see here for us, we have 2 degrees of freedom, 1 and 3. So 2 plus 1 plus 3, you have 6 degrees of freedom per leg. And here different models, so the forward, the inverse kinematics, the dynamic model, the contact model, and so on. Here I will show you just some videos to show that the simulator is working well. Let's see the first video. So the first video here, it's a squat motion. It's like that. So we ask the robot to do this motion, and pay attention. Look here, as you can see, we have the contact forces with the ground. They are represented by these arrows. If the arrow is big, it means the force is big. The arrow is small, so the force is small. And in real time, you can see the change of the force. Now, the second video here, we can see the whole body motion. We try to do this balance. And also, as you can see here, the change of the contact forces. The point which is in the middle is the position of the ZMP. It's the resultant force regarding the Z-axis. And as you can see, if the force are modified, so this position will move. Now, let's now see the third video. Here we try to do a balance of the arm. So we do a swing of the arm, and we can see also how the contact forces change here, and the ZMP, how it moves. And here inside, you have 2 points, blue and red in the middle. The one, it's the center of mass, and the other one is the ZMP. And look, it's balancing, and it's realistic since it shows what happens on the robot. And even the robot falling down, we can see this on the video normal. The change in forces, the ZMP is outside, up, it's falling down. So this is a realistic simulator that will be used to validate our controllers. And the last video here, we try to move the torso and the arms balance at the same time. So here the torso, as you can see, and the arms. And also we can see the evolution of the contact forces with the ground and the ZMP. Now, the second step, so after we have designed this simulator, the second step was to study the human walking. Human walking, as I said, it's a very complex activity. So to understand the human walking, which is here, can be seen in this video, the contact forces at the same time. And you can have, if you are interested in human walking, you can have this reference. It's a very good book where you can find many things on human walking. So we will have the human locomotion, we have kinematics and kinematics of the human walking. You have energy and muscle activity also during walking, and you have simulation of walking and etc. So it's very good reference if you are interested in study of the human walking. Now, in our case, we try to study the human walking. What will be the tool? What we will use to study this human walking? We have to use a measurement system that will be used to measure or to capture the motion of the human while walking. So in our case, we have used a motion capture system. What is a motion capture system? It's very easy. The concept is to use different infrared cameras around the area where the human will move. The human will be here inside. He will stay inside. And through these cameras, we have to capture the motion of the different joints, the body of the human. Now you can ask me how. It's the camera, but we have to add something. We have to add these reflectors, small parts that will be fixed on the human body. Then we ask the human to move. Then the cameras will localize with precision the motion of each reflector in space. Let's see a demonstration of this system called motion capture.
Welcome to Full Sail University's Motion Capture Studio. My name is Tyron Jordan, course director for Motion Capture. Motion capture is the process of recording and digitizing movement of an object or a person.
Look here, the human, and behind you can see the recorded motion.
Our students learn to work with the technology
You can use it for
to capture active
video
performances
games, for
and refine
instance,
emotion
for movies, for many
to produce
things.
an animated short film. In our studio, we use an
This is the
infrared
cameras.
system. As you can see, we have 23 cameras flooding
23
our volume
around here.
with infrared light. That light gets reflected back to its source using these retroreflective markers.
This is the
The
reflective,
position of the marker is then calculated, placed in
There.
3D space, and recorded.
and you can see behind the
We use
recorded
these
motion.
markers to outline the structure of our subject. In this case, my friend Emil. By placing at least 3 markers on each section of the body, we can accurately define points of articulation or bending points of our actor. Emil is wearing 49 markers, plenty to capture his body.
Measure the position of the markers in real time, and you can see this or reproduce on the screen this motion.
Once the data is recorded and cleaned up, we're ready to go into our animation software. Here in our lab, we transfer the marker information and use it to drive the skeleton of our digital character. The character on our right is our stand-in, and it's directly driven by the marker points we recorded in our studio. The one on the left is our finished version. And as you can see, it's mimicking the motions of our stand-in. The different motion takes are then pieced together and enhanced with animation techniques. As you can see here, we have Emil's fault. We pieced it together with 2 separate running takes. At this stage, we can add details that we couldn't capture in the studio, such as fingers and facial expressions.
Nice. So this is the motion capture system. So we have used this system. Unfortunately, when we did this study a few years ago, we had not this measurement system. So we had a collaboration with Italy, with a research lab called Lab in Italy. And we have made this experience. But actually, we have bought this system and we have it in our lab. So the system that we have used, it includes 10 infrared cameras. In the video you have seen, it includes 23, so it depends on the systems. For this one, it has 10 cameras. And also, pay attention when we have to measure to capture the motion of the human while walking, we need also to measure the contact forces with the ground, to have the position of the ZMP while walking. And for that, we have to use what we call a force plate here. It's just a sensor in the ground. When we walk on this, we can measure the contact forces with the ground, and we use the cameras to localize the markers in the space. Then, from the markers, we can have here the walking of the human, represented by this model, and then we can have more detailed information if we use another software like Life Mode, for instance, where we can have the position of the center of mass in real time, how it evolves. So we made our study and we made some tests on 15 persons, so 15 subjects walking at different speeds. We ask them to walk and we record the motion. We have 35 markers fixed on the body, and we have the Vicon system for the measurement of this position of the markers, and this Life Mode software to measure or estimate the center of mass position in real time. Now, this is the second step for the study of the human walking. The third step now, it's the pattern generator design. So we have proposed firstly basic idea, then we try to see the result. The result was not so good, and we try to modify it to get the good result. So initially we try to apply directly the data coming from the human on the robot. And here, as you can see, is the result. Here, the result, as you can see, the motion, the walking motion is unstable. So the robot will fall down if we apply it on a real robot. Why? Because as you can see, the ZMP, it's outside sometimes from this polygon of support, so it was not so good. And we have proposed, in this case, another solution where we will distinguish the trajectories of the lower body than the upper body. So for the lower body, we have used a very simple model. It's the inverted pendulum model. It's a model very well known in the literature, 3D introduced by Kajita. And we used this model to reproduce the trajectories for the lower body. And for the upper body, we applied the same as the human. And then we tried to validate on this 22 degrees of freedom model. And this is the trajectory, the pattern generator proposed. And as you can see, this is the result. Previously, we have seen that the ZMP from time to time it's outside. As you can see here, the ZMP is all the time inside. So the blue one, it's the single support phase, like that. So he's still inside. And the red one is double support phase. So it's still also inside because the polygon of support in the double support phase, it will be this. Nice. And it's dynamic walking. Why? Because the projection of the center of mass, the first picture, is outside from the polygon of support, so from time to time. So this is the obtained result. And we had the stable dynamic walking. Here it's just the trajectories that have been obtained on the different joints. On the arm joints, then the leg joints, and now the fourth step concerning the controller. We have studied the human walking. We have studied the we have prepared the simulator. We have studied the human walking. We have worked on the pattern generator. Now about control. So as I said before, we have proposed an original control architecture, hybrid, kinematic, dynamic, and the idea is the following. As I said, if you see the literature of walking control in biped robots or humanoid robots, mainly we consider there is two approaches. So the first one is, for instance, to distinguish different phases of the walking, so the single support, the double support, the impact, and so on, and to design each controller for each phase. And then they try to keep the stability of the whole cycle. So this is one solution. There is also other solutions based on the human data. So they do the same, human walking study, they get the data, and they try to use the data on the humanoid robot. The problem, we have different problems in this case, the problem of scaling, because the size of the human and the size of the robot, they are not the same. So you cannot apply directly the measurement on the human on the robot. So this is one thing. And also another thing which is very important is the number of data. So they use a huge number of data. I mean, if you use all the joints, you will have a huge number of data to be applied on the robot. So in our case, we try to develop a basic idea, which is very simple, which is hybrid, kinematic, and dynamic, and we try to use the minimum of data coming from the human walking. And the minimum data that we have chosen are only two. The two data that we need is the position of the center of mass, so the evolution of the center of mass during walking, and the distance between the two legs, between the two feet. It's the relative distance while walking, so just this distance, and the center of mass. And the proposed idea is just to use these two, so the distance between the two legs of the robot and the center of mass, and we try to reproduce this on the humanoid robot. So this is the proposed solution. This is the task form, the kinematic control, and for the dynamic control we add here, as you can see, the ZMP, a closed loop for the ZMP for the dynamic walking, and we arrive here to the implementation. So we have tested this controller on different robots, and I will show you some results. Here, as you can see, just a simulation. It's the human walking. First of all, we have tried the data coming from the human directly on the robot without any scaling. And look here the difference. The human is walking like that. Look the robot. Why he's walking like that? Do you understand why? Have you an idea? No, for stability, but it's very general stability. There is something which is different from the human and the robot.
Yeah. For the actuador?
What?
Actuadores.
What is that?
Motors.
Sorry? Motors?
Yes.
No. Nice. Very nice. It's the center of mass. You know, the human is bigger than the robot. So the center of mass of the human is higher. So for the robot to have a higher center of mass, what he has to do? He has to do this. If he moves the masses of the arms like that, the center of mass will be higher. So to be able to reproduce the human, he has to do this. So this is first result, but it's surprising, but it's true. It's true that he has to do this to be able to reproduce the human walking. Then, now we try to do a scaling now. A scaling between the human and the robot. And as you can see, now it's walking like that. Like that. He's not moving the upper limbs. And to avoid also, this is not a good walking. So to avoid this, we try to do better, to add some constraints on the upper limbs to have this motion of the upper limbs. Actually, we have tried two scenarios of simulation also. This is the squat motion. It's to repeat this, so we have just to move the central mass up and down. And here it's another scenario where we have tried to do walking in simulation. This is the simulation of Hope 3. As you can see here is the motion up and down for the squat motion. And also here, as you can see, is the scenario of walking. And it's stable, as you can see on the obtained results for the walking. Now, we have validated on Sherpa. This is squat. So for the human, he has to do this. And since in our case, we have validated on Sherpa, he has no upper limbs. So he will do just like that. And this is the result. So here we try to control the central mass, as you will see. And the idea, pay attention, we try to control the central mass while keeping the stability. We have to avoid falling down the robot. And actually, we measure the CMP here, and we guarantee that the robot will be stable. And as you can see here, it's the trajectories that we have obtained. Automatically, they are periodic on the different joints, and also, as you can see through the video, the motion is stable. We have tried also on Hope 3 humanoid robot for different scenarios. First of all, we try to modify the slope of the floor, as you can see, and we don't ask nothing to the robot. We just apply the controller, and look, the robot is modifying automatically its posture to compensate this disturbance. And the idea is to keep the ZMP inside. Look, the ZMP is in blue, and the center of mass is in red. So the ZMP is inside the polygon of support. Second scenario, we try to pull. There is a wire here. It's attached here. We try to pull the robot, and the robot will resist to avoid falling down. And automatically, we have just to keep the ZMP inside. And the third scenario, we try to reproduce the human walking on slope. So we introduce this slope, and as you can see here, you can see the effect of the slope. At the beginning, it's okay. The ZMP and central mass are in phase, but in the end, there is phase lag between the central mass and the ZMP, because there is this slope. And finally, last video, we have tried what we call the postural coordination. This student is from here, from Mexico. So he came for an internship of 2 or 3 months, and he worked on Sherpa. And the idea is to do something like that. So, sorry, I can show you better through the picture. Yes, here. We can move this, or we ask the robot to move like that, to follow this moving, while keeping the stability. Here we reproduce the same concept, just by moving the 2 legs of the robot like that, while keeping the stability, and this is the obtained results. And we made an optimization of these reference trajectories to keep balance of the motion. And this is the obtained result in this case. Here you can see the legs and how they move. So we keep the contact with the 2 legs, and you can see the motors, how they work. So we have just to control the rotation in the ankle of this humanoid robot. Nice, let me now conclude the presentation. So actually, in this lecture, I try to introduce you a problem which is very interesting concerning the humanoid walking control. We try to reproduce the human walking on humanoid robots. So for dynamic walking, since we have static and dynamic, in our case, we try to do the dynamic walking. We have to deal with some problems like gauge generation, robot control. So we have trajectory generation and control. And we have tried to propose some human-based control techniques. So to deal with this, to resolve this problem, you have to deal with some challenges like the high nonlinear dynamics, the high number of degrees of freedom, the hybrid and unstable dynamics of the robot, hybrid because of single support, double support, and so on, and unstable because it's very unstable. We have to keep the stability while walking, and we try to deal with also the stability of the walking. We have proposed the hybrid kinematic dynamic control scheme, and we have validated through different control scenarios or so validation scenarios in simulation and in real time on different platforms, and we have shown also the robustness of the proposed controller. Now to finish, I will give you just a link to my web page. If you are interested to look at the details of this research, I mean the papers, the details on what we have done, you can download the papers on ResearchGate. If you want to see videos, you have this YouTube channel, so there is between 50 and 60 videos, you can see them. My email address if you have any question, and I thank you very much for your attention.
Thank you so much, Ahmed. It was very interesting. So, someone has a question? Someone?
Any questions or remarks? Yes?
I have a question. As we can see, a humanoid robot has many degrees of freedom, so it is a redundant robot. In the sense that, for instance, you can move the center of mass by moving an arm, or both arms, or
Yes,
the chest,
yes.
or the legs.
Yes.
So how do you decide which actuators are going to control in order to keep the center of movement quality inside the...
So, very nice question, and it's coming from specialists in the field. Thank you. So, actually, we have used the task formulation problem. So here we have to define different tasks, and we use exactly this redundancy to validate these tasks. And also pay attention, there is a priority. There is an order of priority. I mean, we put the 4 tasks, and we put the first one is the most important one, the prior one, and then we put the second one, but when we put the second task, we pay attention. We have to avoid any conflict between the second and the first by the projection in the null space of the first task, and we do the same for all the tasks. So when we have to realize all the tasks, normally there is no conflict. But now, for sure, if we add, for instance, the joints in the limits, it will improve the motion, because at the beginning we didn't add the joints of limits. So we obtain a motion like that. It was not good. So we add the limits to limit the motions, so we improve. And the relative degrees, the relative distance between the feet and the center of mass of the primary tasks. Then we add also the torso, also the motion of the torso, to limit or to add a constraint as a task, such that they will improve. And like that, we obtain a good motion. But actually, the motion that we obtained here, it was not enough to keep the stability. So this is just kinematics. So we have to add this. This is the measurement of the contact forces. The ZMP is here. Desired ZMP in the middle of the support polygon of support, and then the PD controller, which is nonlinear, and we add it to the center of mass. Okay? And with this architecture, so kinematic and dynamic, we do the motion while keeping the stability. Any other questions? Yes.
In the same case,
Yeah.
what happens if an external force moves the robot? The hybrid control continues going
Yes.
the same way?
Very nice. Very nice question. I have shown a video, and in this video we had an external force. It's here. It's here. In this video, I have shown different external disturbances. The first external disturbance is moving the ground. The ZMP is here. When you move the ground, the ZMP should move. So the robot should do this to compensate this, to keep the ZMP inside. And the ZMP, look, it's almost all the time in the middle. So this is an external disturbance. And the force that you are talking about, it's just coming. So we attach the wire here, and we pull the wire. Yes, here. It's not very visible, but there is a wire. It's fixed there. And we pull, and the robot has to resist to this external force to keep the stability. So this is a scenario where we have shown the robustness. Any other questions? Yes,
First,
please.
very hard to control about yesterday and today.
Sorry?
About the underwater robots
Huh?
and the biped.
Ah,
Why
right.
hard to control?
Ah, very nice question. I think each kind of system has its specificity. I mean, for both, we have very challenging problems. The very challenging problem in humanoid walking, you know, it's the hybrid aspect. It's this contact with the ground. It's the stability, because we cannot easily keep the stability. If you have a robotic arm, the base is fixed. That's a problem. He will not fall down. But here, the contact is unilateral. He can move in this direction, not the other direction. So at any time, he can fall down. This is very challenging. In the underwater vehicles, the problem is the uncertainties on the parameters. We cannot know everything in the parameters, and the time varying aspects. So you can buoyancy, inertia, many parameters can be time varying. And if you keep the controller as it is, you cannot keep the same performance unless your controller is adaptive or robust enough to deal with this. So concerning the complexity, I think it's the same maybe. Yes. Any other questions or remarks or comments?
I have a question also. I know that in this case, the humanoid robot switching the dynamic model to change the task, for example, are completely different the task of climbing or down stairs than walking or sit to stand task. In this case, it's most difficult to obtain a continuous dynamic model to apply to different kind of tasks.
Exactly.
In this case, what is the limit to obtain this kind of dynamic model?
The limits of the controller or the dynamic?
The controller.
Okay, the solution that we have proposed here is something which is very specific. I can re-explain the basics. I said that in the literature you can find many solutions. They consider each phase alone, and they design a control for the single support phase, for double support phase, and they have to support the external disturbance coming from the impact. In our case, we have, for sure, the model is discontinuous, but the controller, we have no distinction between the single support, the double support. No, the controller is continuous all the time, and it's the same controller working for single support, double support for all the phases. This is the particularity. And the other particularity of the controller is we are using the kinematics and the dynamics. The kinematics, so through the Jacobian and so on, you specify your task force, what you want to do, that this is just between the feet coming from the human motion capture, the center of mass, and the joint angle, the torso. All this information is introduced in the kinematic part of the controller. But if you do this, the limit is the stability. It will not be able to keep the stability because we have nothing telling him that the CMP should be this here or here. So we add another loop, which is dynamic. So in this case, we obtain kinematic dynamic controller. So the structure of the controller is hybrid. It does not mean that it's hybrid in time. No, hybrid it means two kind different. I mean continuous and kinematic and dynamic. This is what we mean hybrid. But the hybrid dynamics in the robot, it's in time. Finish single support phase, discontinuity, and so on. Yes. Yes. Okay, please.
I know that this is only for a human weapon,
Yeah.
but if we want to reproduce the animal movement, the controller is still useful? Or
Yes, yes, I think it will be useful. But potentially the problem will become more complex because, as you have seen, our robot, it has perhaps this size. The human has this size. So the trajectories, it was my trajectories that I showed you. It was on me, I put markers and I record. So the robot is smaller than me and you have seen the result. Now if you take a bird, for instance, animal, bird is much smaller. So we have also to deal with this scaling between the animal and the robot. But also, if we want to do this on an animal, we have to put markers on the animal and ask him to. It's not so easy. So a human, he understands. He tell him, you should stay here. But if you put a bird, he will go outside, and this will not work perhaps. So this is the only thing. But otherwise, the concept should work. Yes, should work. Any yes.
You mentioned that you did some work with the non-robot.
Yeah.
There is also some any development kind of applications
Ah,
or tasks we
yes.
can
Okay. So actually, I didn't present the work on now here. I present just the robot. And what we did on this robot is the following. It's a very simple thing. It's concerning the pattern generation. It's concerning this. The idea that we did is the following. Is to generate dancing motion. So to repeat a periodic dancing motion. So he will move the arms, the torso, but he will keep the two legs in contact with the ground. So he moves like that in a repetitive way, periodic. And we have used just the center of mass for the stability. So we designed some reference trajectories to repeat this motion, which is periodic, and while keeping the center of mass. So we measure for each point the position of center of mass, and we be sure that it is inside the polygon of support, and that's all. So we didn't apply the dynamic motion. It was kinematic, static motion, state.
You got like an open loop, you didn't use the sensors in the...
No, exactly. We have used just a pre-computation of the center of mass, and in real time we had used these reference trajectories to keep the center of mass inside, but we didn't use the contact forces. We used them just to prove that the motion is stable. I mean, a posteriori, we do the motion, we record, and we show the CMP is all the time inside, but we didn't use it in real time as a feedback. Yeah. Any other questions or remarks? Yes, please.
Why use motors and not other actuators?
Why use motors and actuators? Give me another example of actuators. If we don't use motors, what we can use?
Pneumatic.
Sorry?
Pneumatic.
Pneumatic. Pneumatic? Yes, there is hydraulic. Yes, this is other kinds of motors. For instance, hydraulic. If you have problems of high forces or high torques, you can use hydraulic. Hydraulic, they can provide very high forces. But in our case, we don't need this. Pneumatic, it's less, but the problem of pneumatic is you have a system to produce the compression of the air, and you need this to be used. We have used this kind of pneumatic actuators, not in this, but in parallel robots. I have presented parallel robots previously. We have designed one parallel robot using this kind of actuators. Okay? Other questions or remarks? Yes, please.
If you compute the movement with a system similar to Kinect that use nuclear points, what could happen?
Okay, yes. I have seen other researchers, they use the Kinect. The Kinect, it's a camera. Pay attention. Here, it's not a Kinect, it's infrared camera. They are different. Pay attention. It's two kind of cameras. But there is some studies. I have been 2 months ago in November in India. It's a motion lab, human-like motion lab, and they use the Kinect. The Kinect, so to capture the motion of the human, and they try to reproduce it on the computer. And their objective is to do what we call the rehabilitation. The rehabilitation for training of the leg, if you have problem of the leg, or for the elderly persons or disabled persons to walk, for instance, they have to do this training. So they have used the Kinect. But in our case, it was not the Kinect, it was the infrared camera. It's the Vicon system. So they are different. Perhaps combining both of them is possible, but it was enough with these Vicon cameras, it was enough. But we can use the Kinect also. Other questions or remarks, comments? No? Thank you.
Okay. Now, the Polytechnic University of Tulancingo grant the following acknowledgement to PhD Ahmed CHEMORI for having given the lecture Walking Dynamic Control Toward to Human-like Walking in the framework of the 10th International Research Congress from the Polytechnic University of Tulancingo, Tulancingo de Bravo Hidalgo, February 14, 2018, Arturo Gil Borja, Rector. Please give a strong applause to him.
Thank you very much for coming.
Universidad Politécnica de Tulancingo. Líderes construyendo su futuro.